Okay, so hi everybody. In this video, I want to show you how to approach problems that have to do with figuring out the limiting resolution of various optical systems. You got a couple of these on your homework assignments, so just wanted to show you how you approach those sorts of things today. So the question asked is this, or the problem is stated like this. A photographer is attempting to take a photo of two ships on the horizon which are separated by a distance L equals 7.8 meters. The camera has an aperture of D equals 1.6 centimeters. Assume the range of visible light is 400 nanometers to 700 nanometers. Here are the randomized variables, the distance between the two boats, and the aperture of the camera. The first part is find the minimum angle of resolution in degrees. Okay, now this is, I just want to say, this is something where the problem solving methods we've talked about actually are quite helpful, because I can easily imagine people going like, oh, I know angles are ratios, so I should take the ratio of these two numbers and figure out an angle from that. This is one of the times that's not going to work very well. So let's follow our procedure again, and we'll do it again over here. What are we looking for? Well, we're looking for theta min. That's what we're looking for. So we could write that down here. We're looking for this thing. Okay, what do we know? Well, we know L and D, those are highlighted, but we also know the range of wavelengths we're looking at, but we're not given a single number, which is a little annoying, but is reasonable actually, because lots of times we want to take color pictures, which have a range of wavelengths. So we know lambda runs from 400 to 700 nanometers. Fine. That's another thing we actually know. And you might not notice that the first time. Again, so we've written down what we know and what we're looking for. We need a relationship between those things. And writing that down helps clarify things. What is the minimum angle of resolution in degrees? Well, we know there's a relationship between the minimum angle of resolution, typically expressed in terms of sine theta min, and what that is given as is 1.22 lambda over D. Okay. What's useful about writing this out is it makes us realize what we have to think about now. If we want theta min using this formula, we need to, what do we need to know? Well, we need D, we're given D, and we also need lambda. We need the wavelength. For this part of the problem, L doesn't enter into it. We're only interested in the angle. So we can ignore that. But we're in this position where lambda is a range, and we're supposed to figure out the minimum angle of resolution in degrees. And this is part of the reason I didn't give this problem to you guys, is because the way this problem is phrased, what do you mean by minimum angle of resolution? Well, the problem with this is, what's the actual resolution in this case? Well, the answer depends on wavelength. If we make the wavelength small, we get a better resolution angle. If we make the wavelength big, we get a bigger minimum angle. Which of these is this asking for? And the problem isn't making it abundantly clear. But in practice, what we often want is, what's the limiting resolution? That is, what is the resolution that's the worst that we can get, that we're going to get with this system? And so we have to think about that. Which of these gives us the worst resolution, 400 nanometers or 700 nanometers? Well, it's 700 nanometers because that'll give us the biggest angle. So that's what I interpret this problem to be. Is that correct? Well, we could try it out. But if you don't think about it this way, you can go down a fairly long road. So what we're looking for is this particular parameter combination. And again, I do want to write this down over here in the spreadsheet because I think it's a little easier to see what's going on. So we can do this calculation for two different wavelengths. So we'll call them lambda 1 and lambda 2. This one is 400 nanometers, so times 10 to the minus. So this one's going to be equal to 400 e to the minus 9. This one is going to equal 700 times e to the minus 9, because we want, this ratio has to be unitless. You have to do it in the same thing. Then we have the parameter d, which we know. That is 1.6 centimeters, so that equals 1.6 e to the minus 2. Fine. And now what we're interested in is this ratio, 1.22 lambda 1, which I'll just write as L1 over D, and 1.22 L2 over D. Okay, we can now sub in these numbers because we have everything we need. It's equal to 1.22, whoops, times this divided by this, or in this case, 1.22 times this divided by this. So we get two different numbers here, both of which are kind of small, 0.000030 or 0.00005. But again, these are sine of theta n. We need to do the arc sine of that, which at least this time there's actually something here for you to do that, but I want to do it explicitly here to remind you of something. We take the arc sine of this number, and we take, whoops, and here, we take the arc sine of this number. This is actually pretty much the same as this. When angles are small, sine of theta roughly equals theta as long as theta is in radians. But we are told to give the answer in degrees. So we have to take the radians answer and multiply it by 1, which is 180 degrees divided by pi radians. And we get two different answers here. So that's what we get for, so we get 0.002 or 0.003 radians. And as I said, I suspect what they're looking, so if we have 700 nanometers, our limiting resolution is 0.003 degrees. If we have 400 nanometers, our limiting resolution is 0.0017 degrees. Now, in practice, this is what matters more, because we want to resolve at all wavelengths. So we need to resolve at the longest wavelength. So it makes sense to me that this should be that. And we'll see if that actually works. Hopefully it will. It gave me the correct answer. So even though it was asking for the minimum angle of resolution, that's because of what it's named, not because of what it's doing. Again, this is why I didn't give this to you guys, because it was not a terribly well-written problem. So theta min is 0.003, and just to be a little more pedantic, 0.306 degrees. Okay, fine. That's knowing that, but that's not the whole problem. We also have this bit, which we'll now expand, where we're told, what is the maximum distance in meters that the ship can be from the photographer to get a resolvable picture? Again, this is a kind of vague statement. What it means is, what is the maximum distance that the ships can be from the photographer to be able to see the two ships are not one ship? You know, if you want a picture with two dark blobs on the horizon instead of one dark blob, that's your aesthetic choice. But that's what this particular problem is asking. So, okay, we now know this, so that's good. So we again go back to our procedure. What do we want? Well, we want the distance to the boats. What do we know? Well, we know these things, and we use this to figure out the relationship, so we can get rid of that. Okay. Now, here is one thing. What relates what we want to what we know? Well, in this case, it's not a particular relationship to any particular bit of physics. This is strictly geometry. We have two boats on the horizon, and I'm going to draw very bad boats. So we have a couple boats here. We know the distance. We know the separation between them is L. And we know that our camera is just barely able to resolve them, and it's some distance away. And since this is a decent camera, I'll try and draw a decent camera, but it's not going to look very good, but that's okay. Okay. And those boats are very small. Anyway. And we know the distance from here to here, that's the thing we're looking for. We're looking for that distance, D. Well, this is, again, a triangle thing. We have lines of sight to these two boats. One of them like that, and one of them like that. This is a length L, and if, depending on how you draw it, you can pretend this is a right triangle with base L, so this distance is L, and this distance is D. And this angle here is theta min. Because we're asked, at what distance does this whole thing work? So this angle is theta min. So this is a geometry problem now, not necessarily a physics problem, but to turn this angle into something useful, we need to use geometry. So to do this, we now need to figure out what's the geometric relationship between these two quantities. And the relevant one is the tan of an angle on a right triangle is the opposite leg, which is L, divided by the adjacent leg, which is D. Now, you might say, wait a minute. What if I didn't arrange for this to be the right angle? What if they were offset a little bit? Well, the thing is, those sorts of criteria don't really matter in this case because theta min is so small. If we had not quite tan theta min, if we had to throw in a couple of extra angles here, it turns out it doesn't matter. It's still basically the case that theta min, since tan theta min roughly equals theta min, that theta min is L over D, as long as theta min is measured in radians. If you measure an angle in radians, then it's a unitless quantity, and like this ratio is fine. If you have this in degrees, this ratio doesn't work. This only works if you have this measured in radians, which we do over here. So we know theta min, we know L, so we can solve for D. We just multiply both sides by D, and you get D theta min equals L, and then you divide by theta min, and you get the final expression, which I'll write over here. D is L over theta min. And this is an expression that makes sense because you can check it quick. Because it's really easy when you divide things out quickly that you flip things around. If you make L bigger, make the separation between the boats bigger, the distance should be larger to be able to see them. You can see them at larger distances. So that makes sense. If you have something with a better resolving power, something where the theta min is smaller, the boats can be farther away before you see them. So hopefully this makes some amount of sense. And so now all we have to do is plug in some numbers. So we can say, we know L is 7.8 meters. It's already in the right unit, so we're happy there. And theta min is real tempted to put in 0.00306, but for this relationship, we need it in radians. So it's 5.3375 e to the minus 5. That's what theta is. Okay, then D is just equal this over this. And what we get? You get a pretty big number. 1.46 e to the 5 meters. Let's see if that's right. It's not right. It is correct. Now, they asked you to do this in meters, but that's a big meters. We can also ask what D is in kilometers. It's just this number divided by 1,000, because there's 1,000 kilometers in a meter. And it's 146. So you can see this, that there are two boats separated by 8 meters with a camera like this at a distance of about 100 kilometers. Now, you won't see any detail within the boats, but you could tell that there are two boats there instead of one. And that's just giving you a sense of how this formula can be useful. It's like if you want to be able to distinguish objects, how far away do they have to be with a particular piece of optics? Anyway, hope this is of some use to you, and thank you for your time and attention.